The galaxy is as vast as it is beautiful, and in this edition of Avatars of the Astral World, we'll explore all the details you need to appreciate it truly. What is a galaxy? A galaxy is a gravitationally bound grouping of stars, stellar remains, interstellar gas, dark matter, and dust. The word comes from the Greek term Galaxies, which translates literally to milky, a reference to the Milky Way galaxy that holds the solar system. Galaxies, averaging an estimated 100 million stars, range in size from dwarfs with less than 100 million stars to the enormous galaxies known. Supergiants with 100 trillion stars, each circling its galaxy's epicenter of mass. Galaxies are classified according to their visual morphology as elliptical, spiral, or irregular. Many are believed to have supermassive black holes at their centers. The Milky Way's central black hole, known as Sagittarius A, has a mass 4 million times more significant than the Sun. As of March 2016, GNZ 11 is the oldest and farthest galaxy ever seen. It has a co-moving distance of 32 billion light-years from Earth and is seen as if it existed just 400 million years after the Big Bang. In 2021, data from NASA's New Horizons space probe was used to adjust the earlier estimate to roughly 200 billion galaxies, which succeeded a 2016 assessment that there were 2 trillion or more galaxies in the observable universe overall, and as many as estimated more stars than all the grains of sand on all beaches of the planet Earth. Most galaxies are 1,000 to 100,000 parsecs in diameter, precisely 3,000 to 300,000 light-years, and are divided by distances on the order of millions of parsecs or megaparsecs. For comparison, the Milky Way has a diameter of at least 26,800 parsecs, 87,400 light-years. It is separated from the Andromeda Galaxy with a diameter of about 152,000 light-years, its next most prominent neighbor by 780,000 parsecs, 2.5 million light-years. The distance between galaxies is loaded with a tenuous gas, the intergalactic medium, with an average viscosity of less than 1 atom per cubic meter. Most galaxies are gravitationally categorized into groups, clusters, and superclusters. The Milky Way is part of the local group, which dominates along with the Andromeda Galaxy. The group is part of the Virgo supercluster. These associations are generally arranged into sheets and filaments surrounded by immense voids at the most significant scale. The local group and the Virgo supercluster are in a much larger cosmic structure named Laniakea. The Milky Way. The galaxy we all live in is known as the Milky Way, which is home to the entire solar system. Its name comes from the way it looks from your planet, Earth. The Milky Way is a band of light seen in the night sky. It's formed from stars that can't be identified using just your eyes. The Milky Way looks like a band from the planet Earth because of its disc-shaped appearance that is viewed from the inside of it. Italian astronomer, physicist, and engineer Galileo Galilei first solved the mystery of this beautiful band of light by breaking it down into separate stars with his telescope in 1610. Many astronomers believed that the Milky Way was home to all of the stars in the universe until the early 20s. After the Great Debate of 1920 between the astronomers Heber Curtis and Harlow Shapley, Edwin Hubble both discovered and proved that the Milky Way is just one of many galaxies in the great beyond. You can see the Milky Way from Earth using just your eyes, and it looks like a hazy band of white light, about 30 degrees wide, as it arches across the night sky. When looking at all the stars at night, all the stars visible in the sky are a part of the Milky Way. That's why the term Milky Way is limited to this band of hazy light. The light comes from the collection of undetermined stars and other materials found in the galactic plane's direction. Dark regions are also inside the band, known as the Coalsack and the Great Rift. These areas appear darker because interstellar dust blocks the light from faraway stars, the region of sky that the Milky Way shadows are known as the zone of avoidance. The Milky Way isn't very bright in appearance, it's relatively dim. The more background lights are present, and even moonlight can make it difficult to see. Because of this, the Milky Way can be super hard to see from brightly lit cities or even suburban areas. If you want to see it without a telescope, it's best to check it out from rural or unpopulated areas while the moon is below the horizon. It is believed that more than 1/3 of Earth's population can't see the Milky Way from their homes due to all of the artificial light. When you're looking at the Milky Way from Earth, the part of it you can see is home to 30 constellations like the Big Dipper and more. The galactic center of the Milky Way can be found in the direction of Sagittarius. That's where the Milky Way is at its brightest. From Sagittarius, the white light band looks like it's passing around to the galactic anticenter in Auriga. The band then keeps going along the rest of the way around the sky before returning to Sagittarius. This divides the sky into two nearly equal hemispheres. The Milky Way is the second largest galaxy in the local group. Its stellar disk is approximately 100,000 light-years, or 30 kiloparsecs, in diameter and, on average, about 1,000 light-years, or 0.3 kiloparsecs thick. The Milky Way is approximately 890 billion times the mass of the Sun. In March 2019, astronomers reported that the size of the Milky Way galaxy is 1 trillion solar masses within a radius of about 129,000 light-years. That's over twice as much as it was in earlier studies. This study suggests that 90% of the galaxy is made of dark matter. Dark matter is matter that doesn't appear to interact with visible electromagnetic radiation, such as light, so it is undetectable by existing astronomical instruments. The Milky Way is home to anywhere from 200 to 400 billion stars and at least 100 billion planets. It's tough to get an exact number of stars because it would depend on counting all of the very low-mass stars, which are super hard to detect, especially at distances of more than 300 light-years from the Sun. The Milky Way has 4 primary spiral arms. They are known as Sagittarius, the Norma and Cygnus arm, Perseus, and Scutum crux. Outside the Milky Way's gravitational influence is known as the galactic bar. The stars in this bit of the Milky Way are organized into several spiral arms. These unique spiral arms usually contain a higher density of interstellar dust and gas than the galactic average. These arms are also home to a higher amount of star formations. A simulation published in 2011 suggests that the Milky Way could have gotten its spiral arm structure because it kept colliding with the Sagittarius dwarf elliptical galaxy. Some scientists believe that the Milky Way has 2 different spiral patterns, an inner one that was formed by the Sagittarius arm, which rotates fast, and an outer one that was developed by the Carina and Perseus arms, whose rotation velocity is slower and whose arms are tightly wound. The galactic disk of the Milky Way is surrounded by a halo of old stars and globular clusters known as the stellar halo. About 90% exist within 100,000 light-years of the Milky Way's galactic center. Around 40% of the Milky Way's clusters are in retrograde orbits. That means they move in the opposite direction from the Milky Way rotation. Even though the galactic disk contains dust that makes the view hard to see in some wavelengths, the halo part of it isn't. Forceful star formations occur within the disk, especially its spiral arms, which show areas of high star density but don't happen within the halo because there is only a little bit of cool gas to collapse into stars. You can also find open clusters primarily in the disk. Discoveries in the early 21st century have added many things to what was already known about the way that the Milky Way is built. The possibility of the disk of the Milky Way broadening out farther than scientists initially thought has become apparent. This possibility is made credible by proof gained from the discovery of the Cygnus arm's outer arm extension and of a comparable extension of the Scutum Centaurus arm. Another halo has also been discovered. Alongside the stellar halo, the Chandra X-ray Observatory, XMM, Newton, an X-ray space observatory launched by the European Space Agency, and the Suzaku satellite have found a gaseous halo that's made up of tons of hot gas. This recently found halo stretches for hundreds of thousands of light years. That's much farther than the stellar halo. The size of this hot halo is almost equal to the mass of the Milky Way itself. The temperature of this halo gas is between 1.8 and 4.5 million degrees Fahrenheit. The Sun can be found near the inner rim of the Milky Way's Orion arm, in the local fluff of the local bubble and the Gold Belt. According to astronomers who performed studies of stellar orbits around Sagittarius A in the year 2016, the Sun is located at an estimated distance of 27.14 kilolight-years from the galactic center. The Sun is currently 16 to 98 light-years above, or north of the central plane of the Milky Way's galactic disk. The distance between the local arm and the next arm out, the Perseus arm, is about 6,500 light-years. The Sun and the entire solar system can all be found in the Milky Way's galactic habitable zone. The Sun's direction travels through space in the Milky Way, known as the apex of the Sun's way or the solar peak. The Sun usually moves towards the star Vega, which can be found close by the constellation of Hercules, at an angle of roughly 60 sky degrees to the direction of the galactic center. The Sun orbits around the Milky Way in an oval pattern, passing through the galactic plane of the Milky Way exactly 2.7 times in orbit. The solar system takes about 240 million years to complete one orbit of the Milky Way. This is known as a galactic year. It is believed that the Sun has completed 18 to 20 orbits during its lifetime and 0.08% of a revolution since the dawn of humanity. The orbital speed of the solar system about the center of the Milky Way is super fast. It clocks in at approximately 490,000 miles per hour, and the Sun moves through the heliosphere at 52,000 miles per hour. At these speeds, it takes about 1,400 years for the solar system to travel a distance of 1 light-year. Modern research. In 1944, Hendrik van de Hulst indicated that microwave radiation with a wavelength of 21 centimeters would be observable from interstellar atomic hydrogen gas. In 1951, it was seen. This radiation is not impacted by dust absorption, so its Doppler modification can be utilized to map the movement of the gas in our galaxy. These observations led to the hypothesis of a rotating bar system in the center of our galaxy. Hydrogen gas could also be traced in other galaxies with enhanced radio telescopes. In the 1970s, Vera Rubin found a discrepancy between observed galactic rotation speed and that predicted by the visible mass of gas and stars. Today, the galaxy wheel problem is thought to be clarified by the presence of large amounts of unseen dark matter. Starting in the 1990s, the Hubble Space Telescope produced improved observations. Among other things, its data helped confirm that the missing dark matter in our galaxy could not consist exclusively of naturally faint and small stars. The Hubble Deep Field, an extremely long exposure of a relatively empty part of the sky, supplied proof that there are about 125 billion galaxies in the observable universe. Improved technology in detecting the spectra invisible to humans, radio telescopes, infrared cameras, and X-ray telescopes permit the detection of other galaxies that Hubble does not see, notably surveys in the zone of avoidance. A 2016 analysis published in the Astrophysical Journal, led by Christopher Consolis of the University of Nottingham, employed 20 years of Hubble images to assess that the visible universe possessed at least 2 trillion galaxies. However, later observations with the New Horizons space probe from outside the zodiacal light reduce this to roughly 200 billion. Shell galaxy. A shell galaxy is an elliptical galaxy where the stars in its halo are positioned in concentric shells. About 1/10 of elliptical galaxies have a shell-like configuration, which has never been regarded in spiral galaxies. These structures are believed to form when an enormous galaxy absorbs a smaller companion galaxy. Then as the two galaxy centers approach, they start to spin around a center point. The oscillation produces gravitational ripples creating the shells of stars, similar to waves extending over the water. Spirals. Spiral galaxies look like spiraling pinwheels. Though the stars and other visible material in such a galaxy lie mainly on a plane, the bulk of the mass in spiral galaxies exists in an approximately spherical halo of dark matter which stretches beyond the visible part, as demonstrated by the universal rotation curve concept. Spiral galaxies consist of a rotating disk of stars, interstellar medium, and a central bulge of generally older stars. Extending outward from the bulge are relatively bright arms. In spiral galaxies, the spiral arms do have the form of approximate logarithmic spirals. This pattern can theoretically result from disrupting a uniformly rotating mass of stars. Like the stars, the spiral arms spin around the center, but they do so with regular angular velocity. The spiral arms are considered areas of high-density matter, or density waves. As stars move through a component, the space velocity of each stellar system is modified by the gravitational force of the higher density. The rate returns to normal after the stars depart on the other side of the arm. This effect is akin to a wave of slowdowns moving along a highway full of moving cars. The components are visible because the high density facilitates star formation, harboring multiple bright and young stars. Bored spiral galaxy. Most spiral galaxies, including our Milky Way galaxy, have a linear, bar-shaped band of stars that spreads outward to either side of the core, then blends into the spiral arm structure. Superluminous spiral. Recently, investigators conveyed galaxies called superluminous spirals. They are massive, with an upward diameter of 437,000 light-years, compared to the Milky Way's 87,400 light-year diameter. 340 billion solar masses generate significant ultraviolet and mid-infrared light. They are believed to have an advanced star formation rate around 30 times quicker than the Milky Way. Interacting galaxies. Exchanges between galaxies are routine and can play an essential role in galactic evolution. Near misses between galaxies result in warping distortions because of tidal interactions and could cause some interaction of dust and gas. Crashes ensue when two galaxies pass straight through each other and have good relative speed not to combine. The stars of interacting galaxies usually don't crash, but the dust and gas inside the two forms interact, occasionally initiating star formation. A collision can harshly contort the galaxy's shapes, creating bars, rings, or tail-like networks. At the extreme of exchanges are galactic unions, where the galaxy's relative momentums are inadequate to allow them to pass through each other. Instead, they gradually merge to form a single bigger galaxy. Mergers can result in substantial changes to the galaxy's original morphology. Suppose one of the galaxies is much more massive than the other. In that case, the result is cannibalism, where the more significant, larger galaxy remains relatively undisturbed and the smaller one is torn apart. The Milky Way galaxy is now cannibalizing the Sagittarius Dwarf Elliptical Galaxy and the Canis Major Dwarf Galaxy. Starburst. Stars are created within galaxies from a cold gas reserve comprising giant molecular clouds. Some galaxies have been observed to form stars at an exceptional rate, known as a starburst. If they continue to do so, they will consume their gas reserve in a period less than the galaxy's lifespan. Hence, starburst activity usually lasts only about 10 million years, a relatively brief period in a galaxy's history. Starburst galaxies were more common during the universe's early history, but still contribute an estimated 15% to total star production. Starburst galaxies are distinguished by dusty concentrations of gas and the formation of newly formed stars, including massive stars that ionize the surrounding clouds to create H2 regions. These stars produce supernova explosions, expanding remnants that interact strongly with the surrounding gas. These outbursts trigger a chain reaction of star building that spreads throughout the gaseous region. The activity ends only when the available gas is nearly consumed or dispersed. Radiogalaxy. A radiogalaxy is a galaxy with giant areas of radio emission stretching well beyond its observable form. These active radiolobes are powered by jets from their active galactic nucleus. Radiogalaxies are categorized according to their Fanneroff-Riley or FR classifications. The FR1 class is a minority class, low luminosity sources exhibiting structures usually known as plumes, which are much more elongated. The FR2 class is the most typical, showing large-scale systems named lobes. These are double, often fairly symmetrical, approximately ellipsoidal structures on either side of the active nucleus. Active galaxy. Some detectable galaxies are classified as active if they have an active galactic nucleus, or an AGN for short. A considerable amount of the galaxy's total energy output is radiated by the active nucleus rather than its stars, dust, and the interstellar medium. There are numerous varieties and naming schemes for AGNs. Still, those in the lower luminosity ranges are called Seyfert galaxies, while those with luminosities much more significant than the host galaxy are known as quasi-stellar objects or quasars. AGNs release radiation throughout the electromagnetic spectrum from radio wavelengths to X-rays. However, some of it may be sponged by dust or gas related to the AGN itself or the host galaxy. The traditional model for an active galactic nucleus is based on an accretion disk that forms around a supermassive black hole at the galaxy's core region. The radiation from an active galactic nucleus results from the gravitational power of matter as it falls toward the black hole from the disk. The AGN's luminosity relies on the supermassive black hole's mass and the rate at which matter falls onto it. In about 10% of these galaxies, an opposed pair of active jets ejects particles from the galaxy core at speeds close to the speed of light. The instrument for producing these jets is not well comprehended. Blazars. Blazars are active galaxies with a relativistic jet pointed in the direction of Earth. A radio galaxy casts radio frequencies from relativistic jets. A cooperative model of these active galaxies explains their distinctions based on the observer's position. Liners. Low ionization nuclear emission line regions, liners are possibly related to active galactic nuclei and starburst areas. Weakly ionized elements dominate the emission from liner-type galaxies. The excitation sources for the weakly ionized lines include post-AGB stars, AGN, and shocks. Roughly one-third of nearby galaxies are classified as having liner nuclei. Seyfert galaxy. Seyfert galaxies, along with quasars, are one of the two largest groups of active galaxies. They have quasar-like nuclei, very luminous, remote, and bright sources of electromagnetic radiation with very high surface brightnesses. However, unlike quasars, their host galaxies are noticeable. Seyfert galaxies account for about 10% of all galaxies. Seen in observable light, most look like normal spiral galaxies. Still, when examined under other wavelengths, their core's brightness is equal to the brightness of whole galaxies the size of the Milky Way. Formation and evolution. Galactic formation and evolution is an active area of research in astrophysics. Formation. Contemporary models of the appearance of galaxies in the early universe are based on the lambda cold dark matter model. About 300,000 years after the Big Bang, hydrogen and helium atoms started forming in an occurrence called recombination. Nearly all the hydrogen was neutral, non-ionized, and readily absorbed light. No stars had yet formed. This period has been called the Dark Ages as a development. It was from thickness fluctuations or anisotropic abnormalities in this primordial matter that larger systems started to appear. As a result, masses of baryonic matter started to concentrate within cold dark matter halos. These primordial structures ultimately became the galaxies we see today. Early galaxy formation. Evidence for the formation of galaxies very early in the universe's history was discovered in 2006, when it was found that the galaxy IOK-1 has an unusually high redshift of 6.96, corresponding to just 750 million years after the Big Bang, and making it the most distant and earliest to form galaxy seen at that time. While some scientists have claimed other objects, like Able 1835 IR 1916, have more elevated redshifts and therefore are caught in an earlier stage of the universe's evolution, IOK-1's age and composition have been more reliably established. In December 2012, astronomers reported that UDFJ 3954628 is the most distant object known and has a redshift value of 11.9. The thing that is gauged to have existed around 380 million years after the Big Bang, about 13.8 billion years ago, is about 13.42 billion light travel distance years away. The existence of galaxies soon after the Big Bang suggests that protogalaxies must have grown in the so-called Dark Ages. As of May 5, 2015, the galaxy EGS ZS 81 is the most distant and earliest galaxy measured, forming 670 million years after the Big Bang. The light from EGS ZS 81 has taken 13 billion years to reach Earth and is now 30 billion light-years away because of the universe's expansion over 13 billion years. On August 17, 2022, NASA released a large mosaic image of 690 individual frames, taken by the near-infrared camera NIRCam on the James Webb Space Telescope JWST of numerous very early galaxies. Some early galaxies observed by JWST, like CEERS 93316, a candidate high redshift galaxy, have an estimated redshift of approximately Z equals to 16.7, corresponding to 235.8 million years after the Big Bang. The detailed procedure by which the earliest galaxies formed is an open question in astrophysics. Theories can be divided into two categories, top-down and bottom-up. In top-down correlations, such as the Egan-Linden-Bell-Sandage ELS, model protogalaxies form in a large-scale simultaneous collapse lasting about 100 million years. In bottom-up theories, such as the Searles-Esses model, small structures, such as globular clusters, form first, then several such bodies accrete to form a bigger galaxy. Once protogalaxies began to form and contract, the first halo stars called population 3 stars appeared within them. These were composed almost entirely of hydrogen and helium, and may have been more massive than 100 times the Sun's mass. If so, these massive stars would have quickly consumed their fuel supply and become supernova, releasing heavy elements into the interstellar medium. This first generation of stars reionized the surrounding neutral hydrogen, creating expanding bubbles of space through which light could readily travel. In June 2015, astronomers reported evidence for population 3 stars in the Cosmos Redshift 7 galaxy at Z equals 6.60. Such stars are likely to have existed in the very early universe, for instance, at high redshift. They may have started the production of chemical elements heavier than hydrogen needed for the later formation of planets and life as we know it. Evolution. Fundamental structures started to appear within a billion years of a galaxy's formation. Globular clusters, the central supermassive black hole, and a galactic bulge of metal-poor population 2 stars form. The creation of a supermassive black hole appears to play a crucial role in vigorously controlling the growth of galaxies by limiting the total amount of extra matter added. During this early period, galaxies experience a significant burst of star formation. The accumulated matter settles into a galactic disk during the following 2 billion years. A galaxy will continue to absorb infalling material from high-velocity clouds and dwarf galaxies throughout its life. This matter is mainly hydrogen and helium. The cycle of celestial birth and death slowly raises the abundance of heavy elements, ultimately permitting the formation of planets. The evolution of galaxies can be significantly affected by interactions and collisions. Mergers of galaxies were common during the early epoch, and most galaxies were peculiar in morphology. Most stellar systems in colliding galaxies will be unaffected given the distances between the stars. However, gravitational stripping of the interstellar gas and dust that makes up the spiral arms produces a long train of stars known as tidal tails. These formations can be seen in NGC 4676, or the antenna galaxies. The Milky Way galaxy and the nearby Andromeda galaxy are moving toward each other at about 130 kilometers per second, and, depending upon the lateral movements, the two might collide in about 5 to 6 billion years. Although the Milky Way has never collided with a galaxy as large as Andromeda, evidence of past collisions of the Milky Way with smaller dwarf galaxies is increasing. Such large-scale interactions are rare. As time passes, mergers of two systems of equal size become less common. Most bright galaxies have remained unchanged for the last few billion years, and the net rate of star formation probably peaked about 10 billion years ago. Future trends. Like the Milky Way, spiral galaxies produce new generations of stars, as long as they have dense molecular clouds of interstellar hydrogen in their spiral arms. Elliptical galaxies are largely devoid of this gas and form few new stars. The supply of star-forming material is finite. Once stars have converted the available supply of hydrogen into heavier elements, new star formation will end. The current era of star formation is expected to continue for up to 100 billion years. Then the stellar age will wind down after about 10 trillion to 100 trillion years, as the smallest, longest-lived stars in our universe, tiny red dwarfs, begin to fade. At the end of the stellar age, galaxies will be composed of compact objects, brown dwarfs, white dwarfs that are cooling or cold black dwarfs, neutron stars, and black holes. Eventually, due to gravitational relaxation, all stars will either fall into central supermassive black holes or be flung into intergalactic space due to collisions. Larger scale structures. Deep sky surveys show that galaxies are often found in groups and clusters. Solitary galaxies that have not significantly interacted with other galaxies of comparable mass in the past billion years are relatively scarce. Only about 5% of the galaxies surveyed are genuinely isolated. However, they may have interacted and even merged with other galaxies in the past, and may still be orbited by smaller satellite galaxies. Remote galaxies can produce stars at a higher rate than average, as other nearby galaxies are not stripping their gas. On the most significant scale, the universe is continually expanding, resulting in an average increase in the separation between individual galaxies. Associations of galaxies can overcome this expansion on a local scale through their mutual gravitational attraction. These associations formed early as clumps of dark matter pulled their respective galaxies together. Nearby groups later merged to form larger-scale clusters. This ongoing merging process and an influx of infalling gas heat, the intergalactic gas, in a cluster to very high temperatures of 30 to 100 megakelvins. About 70 to 80% of a cluster's mass is in the form of dark matter, with 10 to 30% of this heated gas, and the remaining few percent in the formation of galaxies. Most galaxies are gravitationally bound to several other galaxies. These form a fractal-like hierarchical distribution of clustered structures, with minor associations termed groups. A group of galaxies is the most common type of galactic cluster. These formations contain the majority of galaxies as well as most of the baryonic mass in the universe. To remain gravitationally bound to such a group, each member galaxy must have a sufficiently low velocity to prevent it from escaping. However, if there is insufficient kinetic energy, the group may evolve into a smaller number of galaxies through mergers. Clusters of galaxies consist of hundreds to thousands of galaxies bound together by gravity. Clusters of galaxies are often dominated by a single giant elliptical galaxy, known as the brightest cluster galaxy, which, over time, tidally destroys its satellite galaxies and adds their mass to its own. Superclusters contain thousands of galaxies found in clusters, groups, and sometimes individually. At the supercluster scale, galaxies are arranged into sheets and filaments surrounding vast empty voids. Above this scale, the universe appears to be the same in all directions, isotropic and homogeneous. This notion has been challenged in recent years by numerous findings of large-scale structures that appear to be exceeding this scale. The Hercules Corona Borealis Great Wall, currently the largest structure in the universe found so far, is 10 billion light-years, 3 gigaparsecs in length. The Milky Way galaxy is a member of an association named the Local Group, a relatively small group of galaxies with a diameter of approximately 1 megaparsec. The Milky Way and the Andromeda Galaxy are the two brightest galaxies within the group. Many of the other member galaxies are dwarf companions of these two. The local group itself is a part of a cloud-like structure within the Virgo supercluster, a large, extended structure of groups and clusters of galaxies centered on the Virgo cluster, and the Virgo supercluster itself is a part of the Pisces-Sidus supercluster complex, a giant galaxy filament. Multi-wavelength observation. The peak radiation of most stars lies in the visible spectrum, so observing the stars that form galaxies has been a significant component of optical astronomy. It is also a good portion of the range for following ionized H2 regions and examining dusty arms distribution. The dust present in the interstellar medium is opaque to visible light. It is more transparent to far infrared, which can be used to observe the interior regions of giant molecular clouds and galactic cores in great detail. Infrared is also used to monitor distant red-shifted galaxies formed much earlier. Water vapor and carbon dioxide absorb many valuable portions of the infrared spectrum, so high-altitude or space-based telescopes are used for infrared astronomy. The first non-visual study of galaxies, particularly active galaxies, was made using radio frequencies. The Earth's atmosphere is nearly transparent to radio between 5 MHz and 30 GHz. The ionosphere blocks signal below this range. Large radio interferometers have been used to map the active jets emitted from active nuclei. Radio telescopes can also observe neutral hydrogen via 21 cm radiation, including the non-ionized matter in the early universe that later collapsed to form galaxies. Ultraviolet and X-ray telescopes can observe highly energetic galactic phenomena. Ultraviolet flares are sometimes observed when a star in a distant galaxy is torn apart by the tidal forces of a nearby black hole. X-rays can map the distribution of hot gas in galactic clusters. The existence of supermassive black holes at the cores of galaxies was confirmed